Hi everyone, thanks for being here. My name is Yana Ponomarova. I'm the head of the data science in Capgemini France. And this is Nicolas.
I'm Nicolas Clauden, head of big data architect for Capgemini France also.
So today we would like to talk to you about the extraction of the supply chain relation from the unstructured text, specifically for the application in the oil and gas industry. So as you know, we live in the age of the data explosion, and 80% of this ever-growing data is in the form of the unstructured text. Therefore, there is a lot of value in creation of the automatized solution or automatized readers that would understand the text and that would simplify it and that would bring the insights at the fingertips of the final business decision makers. Search engines do the first steps in this information extraction exercise. However, in my opinion, they don't go far enough. So what if we could create an automated reader, a machine that would structure the unstructured text, bulks of it, and represent it in this structured form, like in this Wikipedia info box, right? But done automatically. Then we could do so many things. For instance, we could process piles of documents and extract a supply chain information from it. And then we could let the final business user query this supply chain graph with SQL-like queries. Or for instance, we could let this machine just analyze through the financial news feeds and let us pop up the alerts about the potentially profitable market states. Or there are so many use cases for that. So I'd like to ask you to think of the interesting relation between the entities that you would be willing to extract, for instance, from your own mailbox. And first thing to do, you would need to realize so that this is the machine learning or information extraction task. So if you're really lucky, the relation that you're looking for would be already annotated for you somewhere, okay? So there are three important databases where you can look for annotations. In our case, we're interested in supply chain information, and unfortunately, we weren't that lucky. So no annotations, we could find no of them. So what we're gonna show you today is the approach, how to do that from scratch, right? So what we want to show you is the extraction of the relationships from patterns, which you can use by itself, or you can use the results of that as the seeds for the further bootstrap approach or the training set for the supervised machine learning afterwards. Okay? So, search for patterns to extract the relations. A very famous approach is to search for Hearst patterns. This approach is used a lot when we want to construct the ontology in a particular domain. So for instance, if you would like to understand the relation between an operating system and Linux, right, this is the hyperonym relationship. And you would be able to find this relation from an unstructured text by looking for patterns X and other Y. For instance, Linux and other operating systems, right? Or X or other Y, etc. There are many more for many more different types of relations. However, supply chain is not one of those, so that wouldn't work. What else could you do? So you could actually look for entities of interest, some particular sites or people, organizations, locations, and infer the relation between those from that knowledge. So for instance, if in the same context you have a location and an organization, you can infer that it is the relation located in that is being talked about. However, not all the relations are this simple. So even if we take person and organization, the relation that can be between those two can be a founding relationship, right? Or it can be an employee and employer relation, right? So this can get even more ambiguous. When we talk about a supply chain, and particularly in the oil and gas industry, we have so many entities of interest that are the sites in this industry, right? Refinery, oil field, pipeline, and so on and so forth. So, and then the directions, they're not so clear. So depending on a product in this industry, the direction of the delivery from one side to another, it could go both ways, right? So we still look for a pattern, but we look for it in a more aggregated and generalizable fashion. So we actually create a graph of a dependency graph from each sentence, and we look for the patterns there, and we're going to show you how. So in order to get this graph, we use Stanford NLP. So Stanford NLP, it is a state-of-the-art natural language processing pipeline that is built on the deep linguistic treatments and machine learning, okay? So it is probabilistic, it is inherently probabilistic, okay? So what we could do if we take a sentence that is up there in the slide, and we could apply a part of speech tagging on that. So that this tool would actually assign a tag to each word, tags such as proper noun, noun, verb, etc. Okay? What else we could do? So there is a already pre-trained named entity recognizer inside of Stanford NLP. So this tool already recognizes 7 particular entities, such as organization, location, percentage, person, and so on and so forth. However, as you can see in this example, it doesn't work so great for our context, right? So it has recognized Saharan crude oil as an organization, which basically means that we have to retrain it and to share with the knowledge of the domain with the engine. And then last but not least, it is the basic dependency parser. It is the component that actually parses the sentence into a graph whose root is the main verb of the sentence. And this is where we're going to look for the patterns. So this is how the functional pipeline for the supply chain relation extraction looks like. So we have embedded the stream of NER, sentence simplification, and relation extraction treatments that are based on the Stanford NLP in the Spark streaming pipeline. We use the batch mode to train the named entity recognizer for the supply chain domain. Okay.
So why are we using Spark? We are using it for 4 main reasons. The first one, we want to reuse some stuff between the batch layer and the streaming layer. The second one, which is probably the most important one, is Stanford NLP is really costly. So what we wanted to do is to distribute every processes to gain some time, of course. We choose to use Spark because we wanted to have the fault tolerant built inside our application and not have to build it. And of course, it was much easier to use Spark streaming than using Apache Storm for our data scientists and developers. And now Yana is going to deep dive inside what we have been doing.
So let's take an example right away, an example sentence that you see on the screen. So after this sentence has been processed by our NER pipeline, it has recognized particular specific entities of interest, such as refinery, in this case, Ezra Refinery. It has recognized that Saharan crude oil is actually a product of oil and gas industry, right? And it has also recognized a pipeline. What is behind this? So in order to look for these recognized entities, we split the sentence. We tokenize the sentence, we split it into words. And we look to annotate each particular word. So as you can see here, in the example of the word oil, the way it is annotated in the final result, it depends on the context around this word. Not only it depends on the properties of the very word, but also on the words around it, okay? So in order to make it true, we need to perform specific feature engineering and also select a model that can do that. So as you can see, we have put on the slide several features that turned out to be very important in achieving this result. Okay, this is not the entire list of the features, but the prominent features are the noun phrase governor. So for For crude oil, that would be oil. For Janaf crude oil pipeline, that would be pipeline. So that would be the noun phrase governor that would infer the sense of the word like Janaf and oil as well. And also, the set of features is forward-looking. So we take up to 6 words to the right, okay? And regarding the model, so we would need the model that allows for this dependence, for this complex dependence on the context. So in order to achieve that, we have chosen the conditional random fields model, which is a sequential model just like an HMM model. However, it has this feature of being a discriminative version of HMM, and therefore it is robust to the violation of the independence assumption between the features, which is exactly what we want in this case. Okay? The next steps of our Spark treatment pipeline are the sentence simplification and relation extraction. So given the same sentence on the entrance, the sentence simplificator, it splits it into 2 independent clauses, such as you see here. So as a refinery processes Saharan crude oil, and Saharan crude oil is piped along a pipeline. So later I'll show why it is so important. And then the relation extraction phase actually does the job of assigning the semantic roles, a supplier, receiver, and a theme, which is an object of a delivery. Okay, so you see specifically it is the second sub-sentence that carries the supply chain information, and therefore the relation extraction actually recognizes that. It recognizes the supplier, the receiver, and the theme properly. How does it happen? So I don't know if you have realized that, but in a language, specifically in English language, of all the words in a sentence, the verb is the very important part of it. It is the word that is at the root of the sentence graph. It is the word that actually gives the sense to the sentence, but not only the sense, it also structures the sentence. So by determining the location and the role of other components of the sentence around the verb, we can realize what roles they take, okay? So let's take the active voice of a sentence, and we split the words, the verbs that can have supply chain meaning into categories. So we use the verb net categorization. So here, for instance, let's take the outgoing verbs such as supply, provide, send, serve, etc. Okay? So in the active voice that contain the root verb in this category, we can parse the sentence. And when we extract the subject from the sentence graph, we can assign the role of supplier to the subject extracted. Okay? Then the object extracted would be either the theme or the object of the delivery, or a recipient, depending on the preposition. Preposition to would mark the recipient, or preposition with in the second example sentence would mark the theme. Okay? In this similar case, we have 6 similar cases, okay, for both active and passive voice that actually create this pattern extraction rules, and all of them are a function of the principal or root verb, okay? However, what happens if the verb that carries the sense of the supply chain is not at the root of the sentence? Like in this case, pipes is actually not the principal verb of the sentence. Then we have the need of sentence simplification. And this sentence simplification is carried out by parsing the dependency tree graph. And therefore, it is very dependent on a version of the Stanford parser, so we have to be careful.
Okay, so about the architecture we have implemented, it's kind of Lambda architecture, but you don't have the server layer, but I'm going to introduce you the batch layer and the speed layer. About the batch layer, so it's on the bottom. You got the document ingestion. They are not moving a lot. It's always the same data, and it's not changing. So we've got the technical description of the oil pipeline, got the historical data, and we have also the contracts. We are ingesting them as with HCP and with NiFi, and we are ingesting them inside HDFS and as a raw data. Then we're going to build some KPIs using Spark, and it's running on our data lake, which is running with Yarn. We are going to structure the data inside the HBase, which is going to be kind of our data warehouse where we're going to plug some tools. We have plugged U and Tableau, and we have built a REST API to publish the results. Now, where did we implement the Stanford NLP? It's in the streaming. So it's in the streaming layer. We are ingesting the documents, such as our partners, the stack and change data, and the engineer's reports. We are moving them inside the 3 blocks that talk about. So we've got two jobs. The first one is the NER prediction, which are extracting the location and stuff like that, as Yana told you. And we have one job which is running both the sentence simplification and the relation extraction. Once we have done the relation extraction, we are putting it inside HBase and inside Elasticsearch to search engine, and also to expose it with the REST API. And we have built some dashboards with Capgemini, and we are exposing some data to our partners, which are filtered. So the thing is, Stanford NLP, as I said before, it's really expensive to use. So that's why we used Spark. And one thing which is really important is you need to build your annotators only once. So when you're doing streaming, you're going to do for each RDD. So this stream is many RDDs. So for each RDD, you need to build only one annotators, which is going to be reused between each RDD, and inside one partition, you're going to instantiate it with a single object, which is kind of singleton in Java. What you want to do is instantiate it with the correct parameters, and you want also to have a method which is, for example, on the right, you have the simplify method, but we have done the same with the relation extraction. Because if we don't do that, for each event, we are going to have about 3 to 4 seconds to process the data. So this is not acceptable. So we need to instantiate only once. We have used Kafka for the streaming. We were diverging between the receiver approach and the direct stream approach. We went with the direct stream approach, which is a new one, which has been built since 1.3 in Spark. Basically, it's great. You have a lot of control on Kafka. The only thing is you won't benefit from the Zookeeper config utilities to track the offsets. So you need to track them yourself. Sorry. Yana is going to introduce some takeaways about data science, and then I will do some about architecture.
So several things you would like to remember when implementing this or a similar natural language processing pipeline. So Stanford NLP is very expensive. However, it is still the richest state-of-the-art linguistic pipeline. And the richest, that's why you want to use it. It is expensive, therefore you want to optimize the way you use it. So it is really interesting to reuse the objects throughout the 3 functionalities above that this pipeline is consisting of. Then it is the way we implemented that relation extraction and the sentence simplification part, very sensitive to changes in the dependency parsers. So be careful about that. Basically, great encouragement to the Spark community to implement the CRF model in the MLlib. It is really the model of natural language processing. So, you know, my greatest encouragement.
Okay, so about architecture and tuning, for architecture, you need to, if you're doing some Kafka, you need to decide on which one you want to use, receiver or direct stream. Basically, what you need to know is, do I need to track the offsets? For deployment, we used Yarn, so one difficulties we have was to decide how to allocate the resources. So you need to allocate with CPU and memory, which is much better because CPU equals more tasks. And we need to do some checkpoints in order not to lose the data. About memory, you're going to need a lot of memory. So in order to have some gains, maybe you should use some serialization. You could use fast utils also, and of course you need to filter as much as possible, but it's been true since Hadoop. So, and as tuning goes, you really need to tune your partitions according to your volume data, and of course prefer data frame as to the RDE. So thank you. Of course, we are hiring in Paris, or maybe on the broad, I guess. And do you have any questions?
For your NLP and entity extraction, did you consider other libraries besides Stanford NLP?
So there exist some libraries besides Stanford NLP, like OpenNLP and some others. The Python libraries are normally based on OpenNLP, right? So in all my experiments, there is nothing I saw that can be compared in the quality of parsing specifically to Stanford NLP. So it is really, you can see a lot of work in deep linguistic semantic treatments in there. And I think other pipelines, they may be beneficial in terms of licenses and for some other reasons. However, in my experience, Stanford NLP has the better quality. It is still probabilistic because there is machine learning behind it, right? So it is not perfect. For instance, sometimes the root word, right, the ship, when you say ship, I want to say that it's a verb, something has been shipped somewhere, right? It can tag it as a noun, for instance, sometimes, because there is a noun. So it is still probabilistic, there are mistakes, but it's still, I think, as good as it gets for now, at this moment. Yeah.
Just a follow-up question to that. So you mentioned that the Stanford NLP is an expensive process. Yeah. So from a Spark perspective, what were some of the techniques that you looked at? Like, did you do caching and things like that? And what were some of the challenges you faced there, and what were some of the steps you took?
Mm-hmm.
So actually, we didn't do any caching. The thing we were looking for in Spark is just the distribution of the fault tolerance. The thing is, Stanford is really expensive. If we wanted to improve it, we would have to rebuild a part of Stanford NLP. So what we have done is just a wrapper, which were implemented with fast utils to gain some time with sentence simplification.
And basically also the object initiation, yeah. It has been done by partition. So we could reuse the object. The most expensive part is actually, well, parsing as well, but the most expensive part is the initiation of.
And what we tried also is reuse the semantic graph between each blocks, but it was not so efficient, so we didn't do it.
Yeah, so we finished with the consecutive maps.
You mentioned domain in the beginning of the presentation. I'm wondering what you mean by domain and how you prepare the domain.
So domain for us, it was oil and gas, right? So in this example, in the very beginning, let me just go to it. Here, right? So the default named entity recognition engine, it has some knowledge. So the way it has been trained and the data that it has been trained on determines what the engine recognizes, what it doesn't recognize somehow, right? So in this way, the organization has been assigned, the tag organization has been assigned to Saharan crude oil, probably because the engine recognizes that the first word that is, for instance, a proper noun, it probably leads to the identification of our organization. So we have retrained that on the data based on the reports in oil and gas industry and the data that we crawled from the web in the oil and gas industry. And the entities that are used in this domain, they have very different properties, right? Very often, it is the location word, right? So for instance, Azure or Saharan, followed by the indicator of the type, right? So it can be, for instance, Ram River Refinery. Ram River by itself, it is basically, it is a river, right? However, it is the refinery that is an indicator. So you need to retrain the model for a particular domain for it to incorporate this knowledge. Yeah.
Wait, and how do you do that? Do you have to label all the, you have to label each part of a bunch of sentences?
Yeah, you have to, you have to create some training sets, yeah, indeed. So basically, it looks very much, your training set would look very much like that. So, and you would then tag each word, right, to a particular tag, and then the engine would understand that consecutive tags of similar type construct a single entity, right? Like here, the Janaf crude oil pipeline, okay? So the weight here of the pipeline, which is the weight of the noun phrase governor, would not be the same as the one that is assigned in the initial default NER engine. So sometimes it is essential. Sometimes for your purposes, maybe that would work brilliantly without retraining. You have to try and see. Yeah.
All right. Thanks for your time, everyone. Looks like we're out of time.
Yeah. Don't hesitate to talk to us after the talk.
Great. Looks like we